Now let's move to process control procedures.
And this is the last part of this chapter. And within this part, we will mainly talk about the statistical process control procedures. All right. So we may still remember in part 2, we mainly talk about the Six Sigma approach, which is widely used in quality management. Right. So further in this part, we will continue to use the Six Sigma approach, and more specifically, we will use the Six Sigma approach within the quality management production or service process. Okay, that's why we will deal with statistical process control procedure within this chapter. All right, and we will mainly talk about 4 different type of situations within the production process, and we will further plot out the process control chart. All right, that we actually mentioned in last part, in the second part, and based on the statistical analysis and the chart that we built up, then we start to look at whether, all right, so whether the situation that we are facing is under control or is out of control. Does manager need to do some reaction based on the based on the monitoring that we will see just in a second. All right, so let's start this part. All right, so first of all, the process control procedure itself is concerned with monitoring quality while the product or service is being produced or is being provided. All right, so basically we test the whole process when the process is being is being conducted. All right, so let's say you are producing a product. Okay, let's say within every hour you can produce, let's say, 1,000, okay, the same products, okay, within a production line. Okay, in order to monitor whether the quality itself is under your control, all right, then for every hour, all right, for every 1,000 units that you produce within that hour, you can, let's say, grab 50, all right, out of them as a sample. Okay, and you start to do some statistical analysis, all right, based on the situation that you are interested about. Okay, we will talk about 4 different situations. Let's say you are interested about one type of the situation, and you do some statistical analysis, and you record it. Okay, for the characteristic of that situation within the process control chart. Okay, and then for every hour, okay, every hour following, basically we can record a dot within that process control chart. Okay, and you can even imagine, all right, for let's say for one day, then basically you can record for let's say 24 different dots, right, from the beginning of this day to the end of this day. Let's suppose this production line will not end; it will actually continue to work the whole day. Then you can record 24 different dots on this process control chart, and then you can see whether these dots are within some certain control or is already out of control. What it means by control? Basically, we'll build up the upper control limit and lower control limit. Okay, if the dot itself is already above the upper control limit or is already below the lower control limit, then probably you have some problem. Or let's say even if it's within the control limit, all right, it actually has some pattern, then we can start to think about what kind of the problem is actually happening, or what kind of the pattern it actually what kind of pattern actually is within this the dots that you actually you can see, right, in order to figure out the underlying reasoning of the quality of those defective products. All right, so this is kind of a little bit abstract if I just describe like this. But gradually, I will repeat this whole process again and again when we are facing 4 different types of situations. But keep in mind, basically, what we are doing here is basically we grab the sample, we capture the characteristic, okay, of every sample, and we plot it out within the process control chart in order to monitor during the whole process. That's the whole thing that we're doing. All right. Okay. So yeah. So for this 4 different situation or 4 different type of problems, actually we can separate into 2 large categories. All right. So here, that's why in this slides you can see that 2 different terms. One is called attributes. One is called variable. So basically, this is actually very simple. All right. So 2 type of actually we have 4 different type of problems or 4 different type of situations. 2 of them is basically measuring some attributes of the quality. Okay, what means by attributes of quality? So basically, for those 2 type of situations, we are measuring the quality characteristics that are classified as either conforming or not conforming. Okay, so basically, those 2 type of situations is more measuring about whether it's good or whether it's good or whether it's bad. Okay. Is this passing the test or is it failing the test? Those kind of qualitative problems. All right. But another 2 type of the situation is basically measuring about the some variability of the quality management. Okay, what it means. So the variable basically is some characteristics that are measured using an actual value. Okay, so actually for those 2 type situations, okay, if we are interested about the, let's say, the mean of the sample or the range of the sample, all right, these are some quantitative issues. Okay, these are some quantitative issues instead of the qualitative issues. All right, so those 2 type of the situations are viewed as the variable situation within the process control problems. All right, so in general, for those 4 different situations, 2 of them are viewed as the qualitative process control problems. All right, or we call it attribute problems. Okay, and another 2 issues within in total 4 different types of situations. We call them variable quality problems. All right, variable quality problems. All right, because they are dealing with some quantitative characteristic of the quality management. Okay, so these are just some give you a big picture about what this process control procedure is dealing with. All right, and then we will start to talk about the 4 different situations one by one. Actually, they are very simple. Just follow me to look through all the things. I think all the process itself, no matter which type of situation, all right, the process itself is very standard. So let's start to move on. All right. So first of all, before actually we start to talk about 4 different situations, okay? But no matter, let's look at this plus. All right, since we say, although we use the Six Sigma approach or we use the statistical approach to analyze, but later on, after we analyze, all right, we get the number of every dots, okay, the number of every dots, and then we will plot it out within the process control charts, all right. And actually, we already described the process control chart in the second video, all right, in the second video of chapter 10. So if you are still unclear about the process control chart, you can go back to the second video and look through it, all right. So let's say, no matter which type of the situation, although we have 4 types of situation, but no matter what type of problems that you are facing, let's just look at the pattern, all right. Let's look at the pattern, all right, and see. Let's say if you are a manager, if you are monitoring the production process or service process, okay, which pattern is normal? Which patterns are not normal? Okay, let's look at those patterns. So let's look at the first one. Okay, it's right here. Okay, so for this pattern, okay, let's say the issue that you are interested about is showing this pattern in front of you. Okay, so by just looking at this pattern, can you figure out some very regular, characteristic of this pattern? Let's look at this. It seems like it goes up, it goes down in a certain way, and then goes up in a certain way, and then goes down in a certain way. Okay, so in this pattern, actually, you cannot clearly figure out what is happening. Okay, for the issue that you are interested about. Okay, so although it shows some variation during this process, right? But it didn't actually show some very regular pattern, okay, of your, of the for the situation that you're interested about, that is dealing with the quality management, right? So in this situation, basically all of the variation itself is called random variation. Okay, and if it's a random variation, basically it means that these are the variations that you cannot figure it out. Okay, for the variation that you cannot figure out, basically, okay, you just you cannot basically use your analysis to deal with it. Then the behavior it shows actually is a normal. All right, it's a normal behavior. You can, because all the variation is random, it's fluctuated, and we know that during this process, during the production process, okay, the fluctuation itself is normal. All right, and if we cannot figure it out, the underlying reasoning, actually, these are the normal behavior. This is a normal behavior. All right, and then let's look at the second one. This one, all right, you see, at the beginning, all right, the dot is showing some fluctuation, and then it goes up, and even above the what? What this line means? Remember, in the process control chart, we talk about 3 different things. Actually, it already shows within this chart. This line, the top line, is the upper control limit. All right. The middle line basically is the mean. All right. And the bottom line basically is what? The bottom line itself is the lower control limit. If this pattern shows that, actually, no matter what kind of situation you're dealing with, all right, since we have 4 situations, 4 different problems, no matter which one, if the dot itself basically coming out from one sample, right? So every dot basically is corresponding to your analysis for one sample. If this dot is already above the upper control limit, it means that, okay, your quality, the issue, you already have some problem within this process, right? It's already out of control. Okay, if you look at the third plot, you see this dot is already below the lower control limit. It also shows some problem. Okay, so basically, no matter the second one, the third one, you already show some warning. Okay, if it happens as a if you are an employee, you are monitoring this whole process, you have to report to your manager and say that, okay, the quality management, the quality, the control procedure already shows some, abnormal thing. Okay, so show some abnormal thing. You may consider to, stop your production process. Okay, immediately. Okay, and try to figure out what is reasoning. Okay, let's say probably if if it's produced by machine, then whether the machine actually have some abnormal behavior, abnormal functionality. Okay, you have to deal with it and then fix it, and then probably later on, when after you fix it, it will go back to a normal behavior like the first one. Okay, but right now, it's not okay. Okay, it's a warning for you. Okay, now let's look at the following one. All right. So let's say for this one actually first of all it's fluctuated, but later on it goes up and also approaching to the upper control limit. So this one actually is very similar as the second one, although it's not already above the upper control limit, but it's already, you see, this is kinetic going up, and this dot is already very approaching to the upper control limit. Okay, so you have to monitor very closely. You have to monitor very closely, because under this situation, this is already a signal. Okay, maybe it's not as severe as this one, but it shows a signal. Okay, and let's say for this one, it's decreasing, and also it's very near to the lower control limit. So you also see a signal that you have to monitor it carefully. All right, and let's look at some other things. Yeah, let's look at this one. All right, you see here for this dot, this is actually very interesting. It goes up, okay, and then goes down. So in general, actually, it shows 2 patterns. It starts, goes up, okay, for within a duration, and then goes down in another duration. Okay. Do you think this is a good thing or bad thing? Think about this. Compared to the normal behavior, do you think this type of the plot is a good thing or bad thing? Okay. The answer to this type of problem is kind of, is tricky. All right. So we can say this is either good or bad, okay, in different aspects. It's bad because, you can clearly see some pattern within this dot, right? It goes up within some duration, and then it goes down within other duration, okay? Maybe, let's say this is plotting us a day operation, all right, a day operation. In the morning, it started to goes up, but in the afternoon, it starts to goes down. Why? All right. So the bad thing is that they show some pattern here, and of course this pattern itself has some characteristic inside, right? It's not like the normal one. Okay, it's bad in terms of this pattern showing up, but this bad thing itself also is a good thing. Why is that? Think about this. Why this bad thing? Why showing this pattern here? It's also maybe it's also a good thing. Why? The reason is that, like we just said in the normal behavior, if everything is normal, okay, if it's like this, it's fluctuating like this, you cannot figure out the reason, right? Because the variation itself probably is just due to the random fluctuation. But here, although we show some pattern, all right, so based on the control, based on the control perspective, it's a bad thing. But it also gives you some indicate that your fluctuation itself is actually following some pattern and it's not random. And since it's not random, you can use it to figure out the underlying reasoning of it. All right. Maybe let's go back to the example just I mentioned. Let's say if it's within 1 day operation, in the morning it goes up, in the afternoon it's going down. All right. You may think about whether the material for the production line in order to produce this product is different within the morning or within the afternoon, or is the temperature is different, all right, during this production process. If you can figure out the underlying reasoning, you can fix it. Of course, you can make the whole fluctuation smooth out. Okay, that'll be very good for you to control your quality management. So that's why sometimes in your quality, especially within this process control procedure, when you control the whole process, production process, especially for the quality management, all right, if you figure out some pattern, okay, it's not always a bad thing. Okay, it's bad in terms of control, but it's good in terms of fixing out the underlying reasoning. Okay, so we have to think about this type of we have to think about this thing in two different ways, right? In two different ways. Okay, so as long as what is normal, in general, we can summarize as this: as long as the whole dot itself, all right, is within the upper control limit, and within the lower control, also within the lower control limit, all right, and it doesn't approach into the upper control limit, or it doesn't approach into the lower control limit, okay, and it's also not actually showing some very clear pattern, okay, even all of the dots is within some control limit, then we call it normal behavior. Otherwise, we have to fix this problem, okay, give the warning, or we need to try to figure out what is the underlying reasoning. Okay, and before we can fix it, before we can try to understand, before we can figure out the underlying reasoning, we may even stop the production line and fix it, and then do it again. Okay, now let's start to talk about these 4 different specific situations. Actually, these 4 different specific situations are very standard. Okay, let's start from looking at the P chart. Okay, what means by P chart? Okay, so let's say you are producing a product. All right, you are inspecting a product, and you have your standard to differentiate whether every unit of product is defective or not. Okay, and if you're interested about whether the item or whether the production or a product or service that you are conducting is either good or bad. Okay, it's either good or bad. If you're interested about this situation, okay, when you are producing a product or when you are providing a service, you can use P-chart. You can do some statistical analysis related to it, and plot out the P-chart to monitor the whole process. Okay, plot the P-chart to monitor the whole process. Let me give you an example. Okay, example which is exactly showing here to illustrate the P-chart. How we actually use the P-chart to monitor whether the product or service that we are producing or providing is either good or bad. Okay, let's look at this. Now suppose in every hour, okay, let's say you produce a product in 10 hours a day. Okay, 10 hours a day, and within 1 hour, let's say you are producing, let's say 10,000 units of products. Okay, 10,000 units of products. You basically just are producing a product in every hour. The number itself is less than 10,000. And for this 10,000 unit products, since you are interested about whether those products, the quality itself is good or bad, then each time within every 10,000 unit of product, you grab a sample. Okay, the units that you will grab is always 300 for every sample. Okay, that's why you see for this 10 hours, okay, although in every hour you are producing 10,000 units, and within the 10,000 units, you grab 300 as a sample. Okay, that's why here you see the number of inspectors is always 300 for different samples. Okay, and since it's 10 samples total, you basically inspect 3,000. Okay, that's very intuitive. All right, and based on your standard, within every sample, including 300 units, you can figure out the number of the defective products. Okay, the number of defective products. Okay, the number of defective products. So let's say if you look at the first row, okay, it shows 10, means that in this 300 units, 10 of those units are viewed as defective products. Okay, because they are not actually qualified the characteristic, the qualified characteristic. Okay, so this is 10, all right. Then the fraction of the defective products can be easily calculated, right? This is 10 out of 300. Then you use 10 divided by 300 to get this fraction defective, which is 0.03333. That's it. Okay, and you can see within other samples, okay, in other samples, although you always inspect 300, but the number of defective product itself is changing all the time. And the fraction of defective products basically is using the number of defective products divided by 300 within that sample in order to get the corresponding fraction defective. All right. So you see all different numbers can be different. Okay, that's it. Then how to build up this process control chart? As I said, process control chart actually have two necessary elements. What are they? Upper control limit and the lower control limit. Okay, so basically, we have to build up the upper control limit and the lower control limit in order to build up the process control chart. Okay, that will be easy for us to monitor, easy for us to look at the whole pattern, right? But normally, what is the upper control limit and what is the lower control limit? Here we give you the whole the equation for it. All right, the upper control limit equals to P bar plus Z times SP. The lower control limit equals to P bar minus Z times SP. Okay, this is actually very simple. Let me give you the illustration. First of all, what is P bar? P bar is right here. P bar is the number of defective products divided by number of observations. Okay, you see, within every sample, we can easily calculate the fraction of the defective products. Right? Just use this 10 divided by 300, use this 8 divided by 300 to get the corresponding values. But here, what is P bar? P bar is the number of defective products within all samples. All right? and divided by the number of observations also within all samples. Let me ask you this question. What is the number of defective products within all different samples? What is that number? You have 10 within first sample. You have 80 within second sample. You have 9 within third sample. What is the total number? You just add all of them up. What is the total? It's 91. It's already calculated for you. Okay, so the number of defective products within 10 different samples, 91. Okay, what is the number of observations in all 10 samples? It's 3,000, right? You inspect 300 for every sample and you inspect 10 samples, so you have 3,000. So what is p-bar? P-bar is 91 divided by 3,000. All right, so the p-bar itself is 0.03033. It's right here. It's 0.03033. So p-bar can be calculated as I just mentioned. Okay, then we also need to calculate SP. What is S? Remember in statistics, S is a very specific thing. It's standard deviation. All right, it's standard deviation. Okay, since we are talking about the SP bar, basically the SP. Here, since we will not require you to figure out the underlying reason of this equation, but once you see within this equation, you basically need the p bar and also need the n. Okay, also need the n. P bar can be get from this equation, right? So you already got this p bar. What is n? N is the number of the samples. How many samples you have? 10, right? You grab 10 different samples. So you use the p bar that you just got from this equation. Okay, n is 10. You plug all the different numbers within this equation, you get SP. That's how you get the p bar and SP. Okay, so after you get p bar and SP, in order to get upper control limit and lower control limit, it's very easy, right? So you plug this p bar and SP into the equation. But you see, no matter UCL and LCL, besides p bar and SP, you also have another thing, which is Z. What is Z? Okay, everyone should know how to get Z, right? If I tell you that we have, let's say, 99 confidence level, or we have 95 confidence level, or we have 90 confidence level, right? You know how to get the Z value within the Z table, all right? I will not repeat it, of course. But if you're still not very clear about how to get this, send me an email, all right? I will tell you some procedure about it, all right? But try to figure out by using the Z table, all right? And normally, if we say, if we want you to calculate Z, either we directly tell you, okay, the Z or the V values that we want you to use within specific problem, or we will tell you the confidence level. And based on the confidence level, you can figure out the Z yourself. Okay, so based on the equation that I just mentioned, you can clearly figure out what is the UCL upper control limit and lower control limit. Okay, and once you figure out the upper control limit, you can build up this line. All right. In this example, you can double verify it. In this example, the UCL basically is 0.06. Okay, 0.06, and LCL is basically, I think here is 0. Okay. Oh, here there is a tricky thing. When LCL itself is a negative number, okay, when it's a negative number, normally we'll just normalize it to 0. Let's say if you finally get the LCL is equals to -1, but you see that basically what kind of problem we are deal with. Use when an item is either good or bad. So basically, there should not actually have a negative number, so we normalize it to 0. That's why here the upper control limit is 0.06 and the lower control limit is 0. That's it. Then how we get the dots in this middle? Every dot, okay, in this example or in this type of the problem, every dot is representing the fraction of defective products. Okay. So in the first sample, what is the fraction of defective products? Simply, it's just 10 divided by 300, which is 0.03333. So 0.03333. Okay. The second one is 0.02667. The third one is 0.03. And then you kind of connect all of those different dots and get this plot. Okay, that's how we use the statistics analysis to get this basic statistical thing, and then plot out the corresponding process control chart. Okay, that's actually very intuitive, and if you but still have some have problem, let me know. All right. Okay, this is just the process that we already mentioned. Okay, please look at this. All right. Okay, now we are jumping into the second type of problem. Okay, although it's the second type of problem, but actually the procedure itself is standard. Although we are talking about another type of issue. All right, we're still using the process control chart. We'll start using the process control chart, but in order to deal with another type of problem. So that's why we call it a different chart. We call it C chart. We call it C chart. Okay, but in order to build up C chart, we still need to figure out what is the upper control limit and what is lower control limit. Although the corresponding equations itself are different. Okay, under this chart, but the standard procedure itself is the same. Okay, now let's look at within the C chart what kind of the problem that we are dealing with. All right, so you see in the first P chart we are trying to monitor how the fraction defective fluctuates, okay, in the production process. Again, monitor how the fraction of defective products fluctuated in the production process. Okay, but here for the C chart, all right, we are trying to monitor how the number of defects per unit fluctuate during the production process. You see the difference? This one is number how the fraction of defective products fluctuate in the production process. But the second one is basically monitor how the number of defects per unit fluctuate during the production process. Okay, so you may wonder why actually monitor the number of defects per unit. Okay, here we further suppose for every unit you may actually have more than one of the defective thing, or more than one of defective characteristic defective thing, or even just defective holes. All right, defective holes. So yeah, let's suppose you can have more than one defective holes, okay, or more than one multi-functional abnormal holes or defective characteristic. All right, then you start to monitor how the number of defects per unit fluctuate during the production process. Okay, since you are monitoring this type of problem, you also need to build up the C chart based on the process control some numbers. All right, so C bar is basically very simple. All right, C bar is the average number of defects per unit. All right, you may still if we go back to the example that we just mentioned. All right, let's say for every hour you produce, let's say 100,000 units. Okay, and within this 100,000 or 10,000 units. All right, and within this 10,000 units, each time you grab 300 as a sample. Okay, so so basically 300 units, right? And you can based on your test, you can calculate, okay, for every unit how many holes you have, and in total within this 300 units how many holes you have. All right, and in order to calculate the average number of defects per unit, how to do it? You use the total number of units, total number of defects within the sample divided by the sample size to get the average number of defects per unit. So which is C bar. Okay, and SP this time is different, right? You see here in the P chart, SP is this equation, but here, in order to measure the average number of defects per unit, SP is equals to square root of C bar. Actually, this is following in the Poisson distribution, but we will not talk about the Poisson distribution in this course, but we just apply this Poisson distribution here. All right, so just remember that SP equals the square root of C bar. All right, and once you get the C bar, and also this, you see the square root of C bar basically here is just the SP, right? It's just SP, and then based on the confidence level that we provide to you, you can figure out Z, or we directly tell you Z. You can build up the UCL and also the LCL, okay, for the C chart. UCL basically just plus this whole thing. The LCL is basically just minus this whole thing. Okay, it's very standard. Let me give you an example here. Let's say you are trying to inspect the holes in a sample of machines. Okay, inspect holes in a sample of machines. Okay, here I give you the data. We grabbed 8 different samples, and within every sample, you inspect 20 different units of the same product. Okay, 20 different units of the same type of product. Okay, and here, let's say for every unit, all right, you can have 0, you can have 1, you can have 2, you can have 3. Basically, you can have more than one holes within just one unit. That's why here, okay, the total holes itself the number can be larger than the number of inspected, the number of products that are inspected, right? Okay, so here you see for every sample, although we always inspect 20 different units, the total holes within this sample, the number itself is different. The number is different, right? The number is different, and then in order to get the C bar, all right. First of all, within every sample, let's say for this 20 units, the total holes is 76. What is the average number of the holes per unit? The average number of the holes within per unit is 76 divided by 20, which is 3.8. Okay. In the second sample, the average number of holes per unit is 82 divided by 20, which is 4.1. Okay, it's very simple. Just use 76 divided by 20 to get the 3.8. But what is the average number of the defective units per unit? How to get this? You add all of the holes across different samples, which is 612, and then you also add up all of the number of the inspected products, which is 160. You use 612 divided by 160 to get this number, which is 3.825. So 3.825 basically is the C bar. And based on C bar, you just take the square root to get the SP, which is 1.956. It's very easy to calculate, right? And let's say if you assume 99% confidence, okay? Since you already go through the B stat, and actually we frequently use the Z table here, you may even remember the 99% confidence, the corresponding Z itself is 2.58, all right? And within this chart, the UCL is basically C bar plus Z times the square root of C bar. LCL is the C bar minus Z times the square root of C bar. You already have everything. You plug it into this equation, all right? You see that the UCL is 8.871, and LCL is basically a negative number. Okay, here again, since this is from reality example, the LCL itself this number itself cannot be negative. It's meaningless. That's why we normalize it to 0. So finally, the UCL is 8.871 to 0. Okay, it's 8.871 to 0 instead of 8.871 to minus 1.22. So negative 1.22 here is not correct. You should normalize it to 0. Okay, that's the second type of chart, the C chart. Now we will start to talk about the last two different charts, which is measured some variable measurement. Okay, which measuring some variable measurement during this process control procedure. Okay, so as we show here, this variable sampling can measure, let's say, a quantifiable or quantitative attribute, such as weight, the length, the diameter of the products. Okay. Remember, in the first P chart, we are dealing with how the fraction defective fluctuates, right? We monitor how the fraction defective fluctuates. In the C chart, we monitor how the number of defects per unit fluctuate. All right, but here, when we go to the X bar chart and R chart, we are further measuring the fluctuation of the some quantifiable attributes. Okay, the fluctuation of some quantifiable attributes. Okay, S bar is corresponding to the mean of the of your sample. R chart is basically corresponding to the range of your sample. okay, of your sample. We will detailedly talk about this. So first of all, before we even start to do the statistical thing and we start to build up chart, we have some normal rule for the samples. Normally, we will keep the size of sample typically small. Okay, not very huge, but 4 or 5 is guideline, but it doesn't mean that it only can be 4 or 5 or 10 or even 20. That's okay. Okay, but why we normally keep the sample size of samples is small means that because when your size of sample is becoming larger and larger, actually it will take more time to do the statistical thing, do the statistical analysis. Okay, but when the size of the sample is larger, it actually has some advantage, right? Think about this. What is the advantage of when your size of sample is going large? It's more representative, right? It's more representative to what? The whole population that you are producing, right? The number of samples. We always keep the number of samples to be, normally we keep it around 25 samples, okay? It cannot be very small. 25 samples is already including many different samples, all right, many different samples. We wanted the number of samples, this number is, it's not huge, but it's at least reasonable, all right? Because remember, we have to kind of make sure that the sample, okay, can estimate or can be representative to the whole population that you produce. Okay, that's why we always keep this number not that small. The frequency of samples. Okay, yeah. So we have to deal with this is trade-off between cost of sampling and the benefit of the adjustment system. Okay, so it's actually related to the cost of it, and yeah. So right now we are not actually mentioning too much about the money cost. All right, here. So, but still remember this is the criteria. Okay, the control limit. Yeah, the general use z equals 3, z equals certain number. So basically, normally we will use the 90% confidence level or 95% confidence level or 99% confidence level. These 3 confidence level are the standard confidence level. Okay, so my suggestion is that normally in the test we will use these 3 different confidence levels. The best thing for you is to kind of just remember the 3 numbers, or write it down, such that in the exam you don't actually need to you don't have need to look back your z table again and again, right? You just write it down and you can use them directly. Okay. Now let's look at the X bar and R chart. Like I said, X bar chart is monitoring how the mean of the samples, okay, how the mean of the samples fluctuates during the production process. Okay. Again, X bar charts monitors how mean of the samples fluctuates during the production process. The R charts monitor how the range of the samples fluctuates during the production process. Okay. Yeah, you see that actually in the statistical analysis, we always we're interested about the mean, we're interested about the range, right? Yeah. So, but you see, X bar chart and R chart is corresponding to different thing, right? X bar chart is monitoring how mean of the sample fluctuates during the production process, and R charts monitor how range of the different samples fluctuates during the production process. Okay. And here, the X bar chart control limit, you see, no matter it's X bar chart or R chart, still we're trying to build up the upper control limit and lower control limit in order to build up the chart, the process control chart, right? But here we have the corresponding equation. Okay, so in the X bar chart, the upper control limit is based on X double bar, something called A2, and R bar. Okay, and let's say in the R chart, you see the upper control limit is based on D4, something called D4 times R bar. Okay, then how to basically get all these different numbers? Okay, A2 and D4, or D3 here shows here A2, D4, D3. These 3 different things is from a reference table. Okay, it's from a reference table. Okay, I will show you this reference table in the next slide. Basically, you can just check it within that table, and then go back, plug into the specific example. All right. Yeah. But X double bar and R bar is calculated. It's calculated by yourself. Let's look at this. Let's say this actually is an example directly from the textbook. Okay, I think this example is very standard. All right, you see, let's say within a sample. All right, let's say you're producing a product. Okay, how many samples actually you right now you grab? Look at this. Look at this information. How many samples? 25, right? 1, 2, 3, 4 until 25. Basically, you grab 25 samples, okay, within this production process. That's it, all right? And let me ask you another question. Within every sample, how many units? How many units you grab? 5, right? You have 5 different units. And you see here are 5 different numbers. 5 different numbers. Let's say, let me give you some context. Let's say you are measuring the length of product. Okay. Let's say you are measuring the length of product. Okay. You grab 25 sample. Within every sample, you have 5 different units. For every unit, you can record its length, right? Let's say for the first unit within the first sample, the length of it is 10.6. The second one is 10.4. The third one is 10.3. The fourth one is 9.9. The last one is 10.2. That's it. All right. And then in the second sample, you have 5 different units. You record the length of it, and by using the same fashion, you can record all of the numbers within different units, within different samples. That's it. Okay. And then, since for X bar, okay, you are monitoring how many of the samples fluctuate during the production process, right? How many of the sample fluctuate during a production process? Let me ask you the first question. What is the mean of the length within the first sample? What is the mean of the length within the first sample? Basically, you just add all these 5 units, 5 different numbers up, add all them up, divide by 5. You get the average X bar within this sample, right? The average X bar within this sample. And then what? So basically, you have every number for every sample, right? Yeah, you have a number, or you have an X bar for every sample, right? Because you record 5 different units within each sample, you add all them up, divide by 5, you can get the corresponding numbers here. But here, what we want is not X bar, it's X double bar. It's X double bar, okay? Why? Because we are trying to monitor what? We're not trying to monitor mean of every sample. We're trying to, we're trying to use, what is X bar? X bar is the mean of different samples. Mean of different samples, okay? Okay, so you have the mean for every sample. What is the mean for different sample? You use the mean. You see, you have a lot of mean here. You add all them up. You add all them up, and then what? Divided by what? Divided by number of samples. What is number of sample? 25. So you add all those numbers here up and then divide by 25 to get the X double bar. The X double bar represents a number, basically represents the mean of the. Actually, we can say that it's the mean of the mean for different samples. Again, X double bar represents the mean of the mean within different samples. Okay, the mean of the mean within different samples. That's called X double bar. Okay. Okay. Then you see here we also need the R bar, right? No matter it's for X bar chart or R chart, it needs R bar. How to get R bar? Very simple. First of all, what is R? R itself represents a range, right? Within the first sample, what is a range? What range means? Range means the distance between the largest unit and the lowest unit. What is the largest length unit within the sample? Obviously, it's 10.6, right? 10.6 is above all these different numbers. What's the lowest number? 9.9. Okay, it's 9.9. So what is the range? The range is 10.6 minus 9.9, which is 0.7. That's how you get it. Again, in let's say in the 7th sample, in this sample, In the 7th sample, what is the largest one? It's 10.4, right? What is the lowest one? It's 9.9. It's 9.9 right here. You use 10.4 minus 9.9. What is that? What is the result? 0.5. This is how you get range for every sample. Okay? This is how you get range for every sample. But what we need is not R for every sample. We need R bar. Basically, it's the mean of the range within different sample. Okay? You get the range for every sample, then you add all them up, divided by 25 to get R bar. So R bar here is 0.6. R bar here is 0.6. Okay, now, no matter for X bar chart or R chart, you already have the X double bar and R bar. Here, you already have the R bar. The thing that you right now you didn't know is this A2 and D4 and D3. Okay, I already say that we can use the reference table, right? Reference table to get the A2, D4, and D3. Here, I show you the part of this reference table. It's right here. You see, A2 is basically, we just call it a factor for X bar chart. The D3 and D4 are the different factors for R chart, right? Different factors for R chart. A2, D3, and D4. Okay, that's it. Now, how to get the corresponding number? It's actually very easy. You see, the reference here is the number of observations in subgroup. Is N. Okay? Number of the observation in subgroup. Or you can say in sample. That's it. The same thing. What is the number of the observation in sample? Okay? If we go back to this example, what is the number of the observations within the first sample? Number of the observations. 5, right? You have 5 different units. What is the number of observations in the second sample? Still 5. So in every sample, you include 5 different units, right? So here, the number of observations in sample is what? Is 5. Okay? If you look at this 5, then you look at what is corresponding A2? 0.58. What is D3? 0. What is D4? 2.11. Everything is ready for you. Okay? As long as you know what is the corresponding number that you need to figure out. Then you look at the corresponding A2, D3, and D4. You plug into this corresponding equation. Okay? You already get the X double bar. You already got R bar, as I just mentioned. Within this reference table, you can get A2, D4, and D3. You plug into these whole different equations. You can get the UCL, LCL for X bar chart, UCL, LCL for the R chart. Okay? This is the corresponding number you get. All right? You see here for 5 units is 0.58 for A2. That's why here is 0.58. All right? And here for D3 it's 0, right? It's 0. And D4 is 2.11. You see, that's why here D3 0, D4 2.11. And based on all the numbers, you can calculate everything you want. Okay? And after you figure out, let's say, the upper control limit and lower control limit for X bar chart, you can start to build up X bar chart, right? This is the upper control limit, the red line. The blue line is the lower control limit. Okay? The lower control limit. Then let me ask you last question, all right? For every dot showing within this middle, all right? What does it represent? What does it represent? Think about this. In the X bar chart, every dot represents the mean of the length within every sample. So for the first dot, what it represents is 10.28. All right, it's the mean of different units within first sample. The second dot represents the mean of different units within second sample, which is 10.17. Okay, which is 10.17. And you plot all dots. Okay, actually, machine can do this. All right, you can plot every dots, and then basically you connect all those dots in order to get this plot. Okay, the same fashion by using by the R chart, R bar chart, right? The R chart. So basically, every dot here is representing your range. That's why here, the first one is 0.7. You see, so the first dot showing here is corresponding to 0.7. Okay, then you plot that out, and you can see that okay here, let's say for X bar chart, it's kind of normal, but it also shows some pattern. Let's say the variation itself becomes a little bit larger here. Okay, it's becoming a little bit larger. You can start to figure out some reason actually. Okay, but for this one, it doesn't actually show some qualitative pattern. But you can clearly see qualitatively we're using different charts to monitor different things. So that's a very important thing. Okay, try to remember for every different chart what is actually monitoring, Okay, so this is the whole thing that we will cover within chapter 10. I know that there's a little section related to acceptance sampling in the end. If you're interested, please look at this, but we will not cover within the exam. Okay, and yeah, I think this is whole thing for chapter 10. And thank you for viewing the whole different 3 parts within chapter 10. And if you have any questions, don't hesitate. Let me know. Let me help you. Go through every problem that you have. And yeah, again, thank you very much.